Hello again, welcome back to Methods of Operations Research course, and we continue our discussion on integer programming formulations. This ILP represents integer linear programming, and we will start learning the solution algorithms for integer linear programming formulations. In our previous lecture, we talked about the relaxations and their uses. And in today's lecture, we will first see a very primitive solution algorithm, which is called total enumeration or complete enumeration. And then we will start learning a very well-known algorithm, the main solution algorithm for integer programming formulations, which is named as branch and bound algorithm. So let's get started. What's total enumeration? Total enumeration is actually a very primitive algorithm, as I told you. It tries all possible combinations of discrete variable values. When I say discrete, it means that integer variables, okay? Sometimes integer restricted variables are called discrete variables. So in total enumeration, we try all possible combinations for these variable values and first identify whether these combinations are feasible or not by checking the constraints, and then we calculate their objective function values and we select the best one. So let's consider this simple example and let me demonstrate the solution procedure. In this example, as you can see, there are three decision variables, x1, x2, and x3. And according to this restriction here, as you can see, all of them are discrete. All of them are integer variables. Okay, so then what are the possible solutions? As I told you, we need to try all possible solution combinations. So if I say x1, x2, and x3, these can take different values. For example, all of them can be 0. And since they are 0 or 1, each of them can take two values, either 0 or 1. So I can write all possible combinations. For example, x1 can be 0, x2 can be 0, and x3 can be 1. And then we may have 0, 1, 0, and 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. These are all possible combinations for these three decision variables. And for each one of them, we can calculate the objective function value. And of course, we need to check whether they are feasible or not. So let's start with the first one, 0, 0, 0. Is this solution feasible? So look at the constraints. For feasibility, you need to check the constraints, and we see that both constraints holds are satisfied with these values. And when you plug in 0, 0, 0 in the objective function, we find the objective function value to be 0. The second one, 0, 0, 1, if you check the first and second constraints, again they are satisfied. And when we plug in this into the objective function, we see that 0, 0, 1 provides us an objective function value of 19. This third one, 0, 1, 0, it is also feasible, and the objective function value is 4. 0, 1, 1, when you check this constraint, when you plug in 1 and 1 here, you will see that this is not a feasible solution. Okay, so this is infeasible. Then the next one, 1, 0, 0 is feasible and the objective function is 7. 1, 0, 1, so 1, 0, 1, according to this first constraint, as you can see, it is infeasible. Okay, and then the next one is 1, 1, 0, so 1, 0, 1, 0, 1, 1, 0. If you look, both constraints are satisfied and the objective function value is 11. And the last one, as you can see, it's infeasible. So these are all the possible combinations of solutions. There are no other possibilities for these three decision variables. And we evaluated all of them. Now we can identify which one is the best solution. We are trying to minimize, okay? Sorry, the objective is maximization. I have written it wrong. This is maximization. Of course, if it is minimization, the best solution will be this one, right? So still we can use the same method, but the original problem it was maximization. There is a typo in the question. Okay, if it is maximization, which one is the best solution? The one with the highest objective function value, the largest objective function value, which is this one. So this is the optimal solution, and it is the only optimal solution. As you can see, we solved this problem using complete or total enumeration. This method is called total enumeration. But there is a problem associated with this solution technique, because you can solve only very small scale problems using this technique. So here, how many combinations, how many possibilities we had? In total, we had 8 possibilities. Why is that so? Because we have 1, 2, 3 decision variables. Each one of them can take 2 values. So the total number of combinations is 2 times 2 times 2, 8. Now consider that we have a problem where there are k binary decision variables. Then what is the total number of combinations? It will be k 2 times 2 times 2. Each one of them will take 2 possibilities, 2 values, and it will be 2 to the power k. So these are all possible combinations in a model where there are k binary decision variables. So for example, if the number of k, the binary decision variables, is smaller, you can solve it. But if k is 100, meaning that there are 100 decision variables, so what is the total number of combinations, total number of solutions? It is 2 to the power 100, or it is 10 to the power 30. Okay, 10 to the power 30 is a very large number. Okay, so you can make a simple comparison. How long would it take to solve a problem by complete enumeration for a problem where there are 100 decision variables? Assume, for example, the fastest computer can do 10 to the power 12 operations per second. Okay, let's say we have a computer which can try 10 to the power 12 of these combinations in 1 second. Okay, so then it means that in total, to evaluate 10 to the power 30 combinations, it will take 10 to the power 18 seconds. And 10 to the power 18 seconds, if you divide it by 60, you will find minutes. If you divide by 60 again, you will find hours. And if you divide it by 24, you will find the number of days. And if you divide it to the 365, you will find number of years. And the number of years is 3.2 times 10 to the power 10 years to evaluate all possible combinations with a computer which can do 10 to the power 12 trials per second. Okay, it would take for this computer to evaluate all possible combinations this much year. And this is why complete enumeration is not useful when the problem size is larger. So we need another method. We need other intelligent methods. And basically we will talk about 2 algorithms in this lecture, in this course. One of them is the so-called branch and bound algorithm, and the second one will be the cutting plane algorithms. But both of these algorithms have the same structure. The general steps of these two algorithms will be the same. We can talk about 3 steps. The first step, in the first step, what we do, we relax. So we are given an integer linear program, we convert it to a linear program by relaxation. So how do we relax it? Simply, we delete the integer restriction on all integer variables. If there are binary variables, we replace these binary variables with these conditions: less than or 0 less than or equal to binary variable less than or equal to 1. Okay? So if it's a general integer, for example, xi greater than or equal to 0, an integer, so it means that this x can take values of 1, 2, 3, and etc. We just remove this integrality restriction, so it can take any real value. If we have a binary decision variable, then we remove this and we replace it by this condition. And in both replacements, we obtain at the end, we obtain a linear programming formulation. Okay, this is the first step. The second step, we solve the linear program. How do we solve it? Of course, we know how to solve a linear program now. The simplex algorithm can solve this linear program. And after solving the linear program, we get some information about the integer programming formulation, about the original problem, whether we say that the original problem is infeasible depending on this solution, whether we will say that, okay, this solution is also optimal for the original problem, or we will compute some bounds for the original problem. These are the uses of relaxations. And depending on this information, we will add some spatial constraints to the original problem, and with these spatial constraints, still continuing with linear programs, we will try to solve the problems. Okay? So when we start learning these algorithms, the branch and bound and cutting plane algorithms, you will see what type of spatial constraints we are adding, and these steps will be more clear. As I told you, there are 2 algorithms that we are going to discuss in this course, and we will start with the first one, which is branch and bound algorithm. Okay? So the branch and bound algorithm, it is developed in 1960s. It is not a very new algorithm. It's an older one, but it's very effective. And of course, the original version of the algorithm and the current version are not the same. The general idea is the same, but it has improved a lot. And we will learn the branch and bound algorithm by solving examples. Okay, so the example problem that we are going to solve is this one. We want to maximize this objective function 5x1 plus 4x2. Subject to, we have 2 constraints, and x1 and x2 are both non-negative and integer. So this is an integer programming formulation. If you want to solve these with complete enumeration, yes, you can do. You can try all possible combinations of these decision variables. But since x1 and x2 now are not binary, they may take many other different values. So you can try 0, 0. Is it possible? Yes. 0, 1, 0, 2, 0, 3. You would try all these combinations. So when it is, for example, 0 and 6, from this constraint, we understand that x2 cannot be more than 6. So then you can try 1 and 1, 1 and 2, and etc. Okay? But still there are many combinations, and it's not as straightforward as the binary case when x1 and x2 are general integers. Actually, we will discuss the branch and bound algorithm for 2 different cases. we will consider first the case where decision variables are general integers. When I say general integers, I am saying that they are greater than or equal to 0 and integer. So we will consider the branch and bound algorithm for this case. Later we will learn how we can use the branch and bound algorithm when the decision variables are binary. So the main idea will be the same, but there will be some slight differences between them. Now let's concentrate on this one. And the algorithm says that in step 1 of the algorithm, we relax this problem. Okay, relaxing means remove this integer restriction. So x1 and x2 are non-negative, meaning that greater than or equal to 0. And this is now a linear program. The remaining part is a linear program, and we need to solve it. Of course, we can use the simplex algorithm to solve it, but since there are just two decision variables, we can use the graphical solution method to obtain a solution to this problem. And let's solve this problem using the graphical solution method. And this figure over here represents this graphical solution method. So x1, x2, this is the first constraint, x1 and x2 less than or equal to 5. And this is the second constraint, 10x1 plus 6x2 less than or equal to 45. Okay, so this shaded region is the feasible region of the linear program. What is the feasible region of the original problem, which includes these integrality restrictions? It is only these black dots. Okay, 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, 1, 2. Only these dots are feasible integer points. But when you remove this integrality restriction, all shaded region is the feasible solution space for the linear program, for the relaxation. Okay, now how do we find the optimal solution for the relaxation? We need to look at the objective function and the improving direction, which is 5 and 4. And if you go in this 5 and 4 direction, it should be something like this. And if you move in this direction, you will identify that the optimal solution for the linear programming relaxation is this corner point over here. And this corner is the intersection of these two constraints when you make them equality. And we find that in this optimum LP solution, we have x1 equals to 3.75, x2 equal to 1.25, and the objective function value is 23.75. Now, after solving this, it says that we need to use the information that we obtain from here, and then if necessary, we need to add some spatial constraints to the original problem. But let's have a look at that, what we know now. When you look at this solution, the value of x1, 3.75, it is not integer. And the value of x2, 1.25, it is not integer. But forget about this solution. Let's assume that when we solve the linear program, we obtain this. x1 is equal to 4 and x2 is equal to 1. If this was the solution for the linear program, what should we say? What would be our conclusion? In this case, our conclusion would be this. Okay, if the relaxed problem is integer feasible, then the optimal solution of this relaxed problem is also optimal for the integer problem. And we will just stop here. We found the optimal solution. That's it. This is the optimal solution of the integer program. That's it. But as you can see in this example, it is not the case. x1 and x2 are not integer. So what's our conclusion? We cannot say that this is an optimal solution. But look at the objective function value, 23.75. What can we say? Let's say that we want to find the optimal IP solution, okay? Optimum integer programming objective function value. We want to find this. And what we obtained the optimum LP relaxation solution, 23.75. What is the relation between these two? From our previous lecture, we should now be able to say that the optimum relaxation solution should be better than the optimum IP solution. And in a maximization problem, when I say better, it means that it should be greater than or equal to. Okay? The optimum LP solution, LP relaxation solution, should be greater than or equal to, in a maximization problem, should be greater than or equal to the optimum IP solution. And it means that this is an upper bound for the integer programming formulation. Okay? And we know now that when we find the optimum solution for this integer programming formulation, its value will be less than or equal to 23.75. That's it. Okay? But the thing is, we don't just want to find this bound. We want to find the exact optimum. So how this branch and bound algorithm proceeds? What should be the next step? The next step is to consider this region. Okay, so the region over here, if you have a look at this one and this one. So look, this is the x1 axis, okay? This one is the x1 axis. And the value of x1 is in the optimal solution 3.75. 3.75 is between this 3 and 4. So as you can see, this point corresponds to this between 3 and 4. Now, we know that the value of x1 should be integer. So it can be 1, 2, 3, 4, 5, and etc. And its current value is 3.75. So in between 3 and 4, x1's value cannot be between 3 and 4. It can be less than 3, or it can be greater than or equal to 4, but it cannot be between 3 and 4. But in the optimal LP solution, it appeared to be between 3 and 4. Now what we do, we add two constraints into our model. And in the first one, the first constraint will say that, okay, let's consider the original LP feasible region, which is this shaded region. And into this one, let's integrate this constraint so that x1's value will be less than or equal to 3. So that we will consider this side of the feasible region. And as a second alternative, okay, we would add to the original feasible region, we would include this constraint and say that x1 is greater than or equal to 4, so that we will consider the other side of the x1's values. So this region in between 3 and 4 will be eliminated. So it means that the next time when I try to solve the linear program, it will not give me 3.75 anymore. Okay, so it will give me the next best. Either the value of x1 will be less than or equal to 3 or greater than or equal to 4. So how do we implement these two constraints? Okay, x1 less than or equal to 3, x1 greater than. Of course, if you implement them at the same time to the same model, they are conflicting with each other. How can the value of x1 be less than or equal to 3 and greater than or equal to 4 at the same time? It's not possible. And of course, we will not add them at the same time. We will add them separately, one by one. So what I mean is this. We have this original feasible region. We solve it and find this value of x1, which is 3.75. Then we add this first constraint, x1 less than or equal to 3, into the original problem. This is an additional constraint now. And we obtain a new LP problem. it is called LP2. We will name it as LP2. LP1 is the original problem and LP2 is the new one. And this LP2 is simply this side of the feasible region, this one. Okay, so what is the difference? The difference is we included a new constraint, x1 is less than or equal to 3. And now we are going to consider this part and try to find the optimum of this. Okay, but we will not stop because there are some feasible points on the other side as well. If we just find the optimum solution of this side, we cannot say that it is the optimum solution of the original model because the original feasible region is this one. We just divided it into two parts. It means that I need to evaluate both sides of this feasible region, find the best integer solution from this left-hand side and find the best integer solution from this right-hand side, and then compare them with each other and select the best one as our solution. So the main idea of the algorithm is this: solve the linear programming relaxation. If it is not integer, if it is integer, stop. You find the integer solution. If the solution is not integer, then divide it into two parts. Add a constraint like this. In this example, we are adding these two constraints. Add a constraint and obtain another LP and solve it. And also add another constraint and have another LP and solve it. And then compare them with each other. Of course, when you solve this one, if it is not integer, again we are going to add some constraints. If it is not feasible, integer, and the remaining problems or the new problems, we will also add some constraints. And as you can see, this shape is like a tree where the root is at the top. It's an upside down tree. So these are the branches of the tree. This is the root, okay, and these are the branches. And what we are doing, we are branching and obtaining a tree. That's why the name of the algorithm is branch. And we will see why it is bound later on, okay? The algorithm name is branch and bound, and it's called branch because of this branching procedure. So now, if we return back to our example, what we had, we solved the LP relaxation. We found the value of x1 to be 3.75, which is not integer. Then we included two new constraints and obtained two new linear programs. And what are these two linear programs? Look, this is the first one, LP2. It has the same objective function value with the original one. These two constraints are exactly the same, but now this one is the additional constraint, x1 less than or equal to 3, and x1 and x2 are still greater than or equal to 0. We don't have this integrality, okay? It's still a linear program. This is one problem. This is the problem on the left-hand side for the feasible region on the left-hand side. And also we need to consider the other case where we include to the original model this x1 greater than or equal to 4. Okay, so these are the two constraints that we included to the original model. Original model is LP1. To this LP1, when we include this constraint, we obtain LP2. To the original model, when I include this constraint, I obtain LP3. And why is this less than or equal to 3 and greater than or equal to 4? Because in the optimal solution of LP relaxation, we had 3.75 as the optimal solution. So we are selecting the integer which is less than this value and the integer which is greater than this value, and say that x1 should be less than or equal to 3 and greater than or equal to 4. If in the solution the value of x1 was not 3.75, but if it was, for example, 11.2, then we would add x1 less than or equal to 11 and x1 greater than or equal to 12 as the constraints, okay? The constraints that we are including to the model depends on the solution of x1, okay? Then we have now two solutions, two problems, LP2 and LP3, and we need to solve them. Which one shall we solve first? We will discuss this later on. You can select any one, okay? But let's solve first this LP2, okay? Again, we will discuss it. It's an important concept, which one to select first and how the solution changes. But as the first case, let's select LP2. Let's solve this one. Okay, LP2 is this one, which means that we are now in this region, okay? And we want to find the optimal solution to this one. Again, using the graphical solution, if we go in this direction, which is the improving direction, okay, this corner is the optimal solution to this LP2. Okay, again, I'm not considering this part now. I am ignoring that part. I will solve it later. On this left-hand side, when I solve it, this is the intersection point, and the optimum solution corresponding to that intersection is this. X1 is equal to 3, X2 is equal to 2, and Z value is 23. Okay, now I need to think about this solution, because this is again a linear program. But when I solve this linear program, there are no restrictions on x1 and x2 to be integers. Okay, there is no such restriction. But still, when I solve it, I obtain this corner, and this corner is already an integer solution, which is x1 3 and x2 2. So what does it mean? On this left-hand side, in this problem for the shaded region, the best LP relaxation solution is the same with the best integer programming solution. So I don't need to consider, I don't need to solve any other problems here. I already find the best integer solution on this left-hand side. This is the best integer solution, okay, that I obtained. That's it. So I don't need to evaluate this left-hand side anymore. I already found its best solution. Now I will do the same thing for this right-hand side. Okay, find the best solution of the right-hand side, best integer solution of this right-hand side, and compare them with each other. And of course, if you look at this right-hand side, there is just one single solution, integer solution, which is this corner, which is 4 and 0. And if you put 4 and 0 into this objective, you can immediately get this Z value of 20 on the right-hand side. And when you compare these two, you see that for a maximization problem, this is better, and this is the optimal solution for the whole problem. But of course, in this example, this right-hand side, on this right-hand side, we had only one single integer solution, but it may be more. Okay, so what should we do? Now we will make a very critical observation. It's very important. Look, in the original problem, when I solved the LP relaxation in the first case, I found this. The IP optimal solution was less than or equal to 23.75. Remember, it was the original solution. And I found this, and it was an upper bound for me. And now I found a feasible solution to my integer problem. This is a feasible solution with an objective function value of 23. So what can I say about this solution and the optimum solution of the IP? So this is the maximum possible. This is only one integer solution. So what can I say between these two? Can I say that this is the optimal solution? No, because I haven't evaluated this right-hand side yet. I'm assuming that I haven't evaluated that right-hand side yet. I only found this solution. So what can I say? So for a maximization problem, any integer feasible solution gives us a lower bound. So the optimum solution will be greater than or equal to this value. So I can write here that the integer programming optimal solution will be between 23 and 23.75. Okay, this is a very critical observation which will lead me to the optimal solution without evaluating this right hand side. Okay, now let's continue our observation. Let's have a look at this problem. In this problem, in the original problem, x1 and x2 are restricted to be integers, right? They can take only integer values. And now look at the objective function coefficients of x1 and x2. Both of them are integers. So x1 is integer, its multiplier is integer. x2 is integer, its multiplier is integer. So this objective function value, can it be something like 23.5 by multiplying integer values with each other and summing them up? Can you obtain decimal values? It is not possible. Okay? This solution, this objective function value must be integer. It is only for this example, but be careful, because if this coefficient was not 5, but if it is 5.1, then the resulting value can be a decimal. But in this example, it is not. It is 5. It's an integer. So the result must be an integer. So what do we know? We know that the objective function value will be greater than or equal to 23. We know that it will be less than or equal to 23.75. And we know that it must be an integer. So what is the value that satisfies all these three conditions? Only 23. Okay? So it means that your optimal objective function value is 23, and which is this solution over here. So I don't need to evaluate this right hand side anymore. Okay? By this observation. And I didn't evaluate it. Why? Because of my bounds. So this is why the algorithm is named branch and bound. Without evaluating some parts, we can just cut that, we can just ignore that, we can understand that that is unnecessary. Okay, so if I show you the example, the solution of this example, this we represent it with such a branching procedure. Sometimes we name this original, so we represent each problem as nodes, okay? And this is called the root node. Sometimes in some books you will see that the root node is numbered as 1, but sometimes it is numbered as 0. It is called node 0. So don't be confused. Okay, it is just numbering. So in this example it is numbered as 1, and this is LP1. When I solve the LP relaxation, I obtain this solution. And since it was not integer, I included two constraints and divided the problem into two parts. These were the constraints. Then I obtained two LPs, LP2 and LP3. I solved LP2 and I obtained this solution where x1 and x2 are integers. So since they are already integers, it means that it is optimum. So I can stop. When I stop a branch, I called it fathom or terminate, okay? Terminate or fathom. And what is the reason of fathoming or terminating? It is because of identifying that this is already integer, okay? Fathom by optimality, we can say, okay? Fathom by optimality. Then, okay, we considered this left-hand side. Now we are going to consider the right-hand side. On the right-hand side, I have this problem, and I need to solve it and decide whether should I fathom it or not. But because of the reasoning that I did, this is a lower bound, this is an upper bound, the objective function coefficients are integers, so I decide to fathom this part as well. And what is the reason for fathoming? Because of bound. Okay, so here I fathomed by finding an integer solution. Here I fathomed or I terminated because of a bound. And then there are no other problems to consider. There were only two alternatives, and it means that this is the optimal solution. Okay, so LP3, as I told you, is fathomed because of this reasoning, and this is the representation. I fathom this part because of optimality, I fathom this part because of bound, and then we stop the branch and bound algorithm, and the optimal integer solution is this one. Okay, this is how the branch and bound algorithm works. So we will continue learning the details of the algorithm and solve more examples in our following lecture.